Okay, so in this video we're going to shift gears and we're going to talk about valence bond theory. So up till now we've been talking about shapes in this chapter, and now we're going to talk about how bonds are actually formed. So when we say valence bond theory, the valence just refers to the outermost orbitals. So covalent bonds formed form from in-phase overlap of orbitals. Don't worry about the in-phase part right now. I'll explain what that means in a second. Let's just look at a simple case. H2. Okay. Each hydrogen has one electron, and those electrons reside in the 1s orbital. So that's what's going to be overlapping. So there's a hydrogen, there's another hydrogen, there's a 1s orbital, there's another 1s orbital. Okay, and in those orbitals, we have an electron. So we bring those guys together, what do we get? We get overlap. And when they overlap, they form a bond. And we give this bond a name. That is a sigma bond. And we just abbreviate sigma like that. That's the Greek letter sigma. Okay, and how does a sigma bond form? Or what's the definition of it? It's just the bond formed from orbital overlap along the axis between nuclei. Okay, what the heck does that all mean? Pretty simple, really. Let me just show you. All it means is that the bond is forming, the overlap is in this region here. That is the axis between the two nuclei, between the two hydrogen nuclei. It'll make more sense when we get to a pi bond, and that is not the case. Okay, just slightly more complicated. Let's do F2. And so in order to understand where the overlap is going to come from in F2, let's look at the electron orbital diagram. 1s, 2s, 1, 2, 3, 2p. This is just for one fluorine. Okay, so the overlap is going to be, the overlap is going to be right there, and those 2p orbitals that only have one electron each. So now this is where the in-phase part comes in. So if we have a fluorine here, and I'll put another fluorine over here, we have half of a p orbital is one phase, and the other half is a different phase. So if you remember back to when we were talking about this, these are like, this thing has a mind of its own sometimes. These are like a positive and a negative. Okay, it doesn't matter which one we call positive, which one we call negative. So you have to have negative overlapping with negative, positive overlapping with positive, or else there's no bond. And of course we have our electrons in here. So what happens when they come close enough together? Well, same thing that happened above. We have our fluorines, and we have overlap there. Maybe a bit exaggerated, but that's okay. And then we have these guys here. That's just the other half of those p orbitals. And we have the electrons occupying that orbital. And what kind of bond is this? Just like above, because the electron density is along the axis, and we can just highlight that, the axis between the nuclei, that's a sigma bond. Okay, and can we have overlap of a different kind? Sure, let's just look really quickly at HCl. Okay, and HCl, and I'm just going to draw the molecule with the overlap. Here's our hydrogen, here's our chlorine. Of course, we have a 1s orbital there, and then we have a p orbital there, and then just the other half of the p orbital. Okay, and we have 2 electrons there. And what type of bond is that? Hopefully you know that it's a sigma bond, because that's the only kind of bond you know right now. Okay, and it doesn't matter that this is a 1s and that this is a 2p. Okay, we still have that in-phase overlap, and that forms a sigma bond. Okay, don't worry, we'll get more complicated.